Sports Introduction. Hi everyone, I'm Azumi Mamiya from Shizuoka University, Japan. Today, I'd like to talk about zero-determinant strategies under observation errors. This is collaboration work with my supervisor, Genki Ichinose. So, cooperation is the basis for building sustainable society. In a one-shot interaction, cooperation among individuals is suppressed because cooperation takes cost to the actor, but defection does not. This cooperation-defection relationship is well captured by the prisoner dilemma game. This is typical payoff metrics of prisoner dilemma. If both players cooperate, they will get score 1. Similarly, if you defect and the opponent cooperates, you will get score 1.5, and the opponent gets minus 0.5. If both players defect, and they will get score 0. Therefore, mutual cooperation is best for the whole, but defection is advantageous for individuals. The matrix on the right shows the general payoff matrix. In the RPD game, R, S, T, and P must satisfy these conditions. In previous study, Memory 1 strategies have been often used. Each player using the strategy decides an action from only the outcome of the last round. Player's strategies is specified by 4 tuples. PCC is the conditional probability that you cooperate in this round when both players cooperated in the last round. Similarly, PCD is the conditional probability that you cooperate in this round when you cooperated and the opponent defected in the last round, and so on. These are the example strategies. In this figure, we fix WLS strategy for you and randomly generated 1000 strategy for the opponent. Each black dot represents the expected payoff relationship between two players. As you can see, the payoff relationships are not linear. In 2012, Press and Dyson suddenly proposed a new class of strategies called Zero-Determinant (ZD) strategies. ZD strategies impose a linear payoff relationship between two players' payoff, irrespective of the opponent strategy. ZD strategies have some subclass strategies. Equalizer can fix the opponent's expected payoff, irrespective of the opponent's strategy. This figure shows the equalizer makes the opponent pay off 0.5. On the other hand, extortion always get higher payoffs than the opponent. You can see extortion gets twice score as much as the opponent. So, in some previous studies, either observation error or discount factor was assumed. By assuming each factor, situation in the real society can be well captured. However, both factors are not assumed at the same time in these studies. In our study, we introduced both observation errors and discount factor on future payoff in two-person repeated prisoner dilemma. And we examine a set of strategies that unilaterally linear relationship on payoff of players, including ZD strategy. In the real society, sometimes you can't see what action opponents take, and the payoff is determined by signals and actions. This case is called imperfect monitoring. We assume there are two retail stores, A and B, and they sell the same product. Both stores set a price and observe the number of customers. This is the payoff matrix in this situation. The actual benefit of the store is determined by the number of customers and the price of goods. For example, if both stores keep the price, and the customer will not be biased towards one store, Therefore, both can sell the product at a high price and can get high benefit. In this situation, sometimes noise from environment makes the signal reversed. For example, unexpectedly, store G opened near store B, and then store B began observing the decrease in number of customers and getting minimum payoff. Here, store B thinks that store A discounted the price as a defection. This is observation error. This is one of the elements we assume. Additionally, we assume discount factor. Discount factor delta is a calculation of the present value of future payoff. The payoff you get in the future is worthless than in present. The discounted payoff is given by ST. The larger T is, the more payoff are discounted. Therefore, the expected payoff is given by S. Here we use this formula when we calculate the present value of future payoff. Let me show you the model. We consider two-person RPD game with observation errors. In our model, the realized payoff for each player depends only on the action he chose and the signal he received. Each player chooses action C or D. Then they can only observe a signal G or B. The signals basically depend on the player's action, but is also affected by noise from environment. For example, a player observes G when the other player chooses action C. However, when an error occurs to a player observes B, although the other player chooses action C. So, let epsilon be the probability that an error occurs to one particular player, not to the other, and xi be the probability that an error occurs to both players. The expected payoff against action are denoted by RE, SE, T, and PE. We assume these conditions of RPD game. We consider two player X and Y that adopt memory 1 strategy. PCG is the conditional probability that X cooperates when X cooperated and observed signal G in the last round, and so on. And P0 is the probability to cooperate in the initial round. Similarly, Y's strategy is specified by Q. The stochastic state of two players in round T is described by VT because both players adopt memory 1 strategy. This figure shows the transition from the state to CC to CD. Then, the stochastic state of two players in round T plus 1 is calculated by multiplying VT and transition matrix M. Therefore, for a discount factor, the player's expected payoff is given by SX and SY. In this setting, we derive a set of strategies that unilaterally linear relationships on payoff of players. We analyze it same way Press and Dyson did. A linear combination of both player payoff can be given by the form of determinant. If the numerator is 0, the payoff relationships are linear. It is easy to find Z strategy can make the numerator 0. It turned out that Z strategy are given by these equations. This figure shows numerical example of ZD strategies, extortion. In our study, we analyzed the numerator further. We revealed that unconditional strategy also makes the determinant 0. This figure shows numerical example of unconditional strategy, or D. As a result, only two types of strategies can enforce linear relationships. Finally, we analyze GD strategies further and derive a threshold value above which subset of GD strategies exist. Since observation errors and discount factor are considered, in general, the ranges in which GD strategy can exist are narrow. As the error becomes larger and discount factor delta becomes smaller, the minimum correlation factor chi-c becomes larger. In other words, GD strategies small chi do not exist. Furthermore, GD strategies do not exist when discount factor delta is small. We reveal that minimum discount rate delta C becomes larger as the error rate is increased. Here's a summary of presentation. Thank you for listening.
Thank you. All right, we have some time for questions if anybody wants to either unmute themselves or raise their hand.
So I maybe have one question. Is this okay?
Yes.
Yes.
So I understand your result correctly. You mean the Dyson's strategy is also possible in a noisy IPD game. But there's a different types of ZD strategy in Dyson's framework, and he said in the noisy situations, which ZD strategy is more effective. I may be wrong catching up your talk, but if you can explain it again, it would be very useful.
If error exists, perfect extortion is do not exist.
So in this case, yeah,
extortion do not win or D.
Okay.
Well, yeah, but my question is because there's a noise and you cannot precisely determine a determinant equals to 0, so that the strategy also has some intrinsic noisy fluctuation or something, right? So it can be effective. Only the Dyson's strategy is very effective when there's a noise. There's no noise, right? So I was just wondering how you can compromise this errorless situations. And you said because one of your strategy extracted from Dyson's strategy is that every probability is COD equals to 0, then you can avoid the situations. Sorry, it wasn't so much clear to me, so that's why I just want to understand correctly.
Yeah, that's a good question. Azumi, if you want to think about it a little bit, you can. We can also take the conversation on the Slack.
Okay. Yeah. Thank you so much. Well,
yeah.
Yeah.
Thank you so much. You did a very good job. That was a really nice talk. So well done. We'll give Azumi one more round of applause.
Thank you for listening.
Yes, of course. All right. Who do we have up next? Let's see here. My little list. All right.